Hubble's last image doesn't hide a monster, it hides a number. And that number is so wrong it could mean cosmology, our best story of the universe, has a missing chapter. Two of the most precise measurements we have disagree by about 9%, 67 versus 73 kilometers per second per megaparsec. That sounds tiny, until you realize it rewrites the universe's timeline. So what is Hubble seeing that the Big Bang model isn't? Here's why this defies everything we think we know. One ruler reads the universe's baby photo, the cosmic microwave background, and predicts today's expansion rate. Another ruler, Hubble, measures the universe right now, using real stars in real galaxies. And they don't match, not by a rounding error, by enough that entire conferences revolve around this one fight. If the early universe ruler is right, the universe expands at about 67. If Hubble is right, it's about 73. You can picture it like this. Two clocks, both built by master engineers, both ticking perfectly. But they disagree on the time by hours. Scientists expected the disagreement to vanish as measurements improved. It didn't. So the question that demands an answer is simple. Is our measurement wrong? Or is our physics incomplete? Here's the normal science. So you feel why this is weird? You can't stretch a tape measure to a galaxy. So astronomers build a distance ladder. Step 1 uses Cepheid variable stars, stars that pulse brighter and dimmer on a reliable schedule. Their pulse period tells you their true brightness. Compare true brightness to observed brightness, and you get distance. That's your first rung. Step 2 uses that rung to calibrate type Ia supernovae, explosions so bright we can see them far across the universe. With distances and redshifts, you infer how fast space expands today, the Hubble constant. Now the other side, the early universe. The cosmic microwave background is the cooled light from the early universe, an imprint of conditions shortly after the Big Bang. Using the standard cosmology model, called lambda CDM, scientists fit that baby picture and extrapolate what the expansion rate should be now. That's where the modern 67 value comes from. And Hubble's local ladder is where the 73 value comes from. This is where things get strange. Because if the model is correct, these two numbers should converge as data improves. Instead, as Hubble's distance ladder got tighter, more Cepheids, more calibrations, more cross-checks, the gap stayed. That's why the last image framing exists. Not literally Hubble's final photograph. Hubble still works, but the most mature, most stress-tested version of its measurement pipeline. And the result keeps landing on the same uncomfortable answer. The universe seems to be expanding faster than the early universe prediction allows. You might be thinking, okay, but space is messy, dust, crowding, instrument error. Exactly. And that's why the first assumption in the field was, Hubble must be wrong. The twist is what happened next. The modern push for Hubble's value is often associated with the H0ES team led by Adam Rees, building precision distance ladders with Cepheids and supernovae. Meanwhile, the early universe value is anchored by Planck's analysis of the cosmic microwave background. First, scientists asked, are Cepheids being misread? Crowded star fields can blend light. Dust can dim stars. Calibration can drift. So the ladder was rebuilt and rebuilt. Different galaxies, different anchors, different error budgets. And the number didn't collapse toward 67. It kept hovering near the low 70s. Then scientists tried another angle. Maybe the early universe inference is off. Because Planck doesn't measure the Hubble constant directly. It measures the early universe pattern, then infers today's expansion rate through lambda CDM. So if lambda CDM is missing a component, Planck could be right about the early universe and still lead to a wrong present-day value. For years, each side could claim the other side's ruler was flawed. And then a new telescope arrived, built to settle arguments like this. Enter James Webb, JWST. Webb sees the universe in infrared with incredible resolution. That matters because one of the biggest criticisms of Hubble's ladder is star crowding and dust. If Hubble was fooled, JWST should catch it. Here's the headline. Early JWST cross-checks of key distance ladder targets did not immediately erase the tension. That doesn't prove new physics, but it makes the Hubble is just wrong escape hatch narrower. The mystery didn't shrink. It sharpened. So what's the main explanation on the table? 3 theories explain this, and none of them are comforting. Theory 1. Measurement bias. Somewhere in the cosmic distance ladder, a subtle systematic error survives every cross-check. That's possible. The ladder is powerful, but it's complex. Theory 2. We live in an unusual neighborhood. If our region of the universe has a different density than average, a kind of cosmic bubble, local expansion could look faster. The idea exists, but it has to match large-scale maps of structure, and the required bubble may be hard to reconcile. Theory 3. New physics. Something about the universe's energy content or gravity is different than lambda CDM assumes. A popular candidate class is early dark energy, a brief extra energy component in the early universe that changes the inferred expansion history. Think of it like a temporary turbo boost. It doesn't dominate forever, but it changes the trajectory enough that the numbers stop fighting. Here's why that's both satisfying and terrifying. It would mean the universe had a behavior we didn't include in our model. Yet our model still mostly worked, so we didn't notice. And that raises the next question. If we missed that, what else are we missing? And don't misunderstand what this means. If the Hubble tension is real, it doesn't automatically mean the Big Bang is fake. Lambda CDM still explains a huge amount. The tension is a crack, not an instant demolition. Just when you think it's a clean 2-number standoff, 67 versus 73, another twist shows up. Other measurement methods don't line up neatly. Some approaches land closer to Planck. Some land closer to Hubble. Some sit in between. That doesn't make the problem go away. It means the universe is forcing us to audit every ruler we own. Methods like the tip of the red giant branch as an alternative distance anchor, strong gravitational lensing time delays as cosmic clocks, and BAO as a large-scale ruler all contribute pieces, sometimes in tension with each other too. So the question becomes, is one method wrong, or are we seeing hints that the underlying model is too simple? Here's where it gets crazy. If the resolution is new physics, it might not be one clean new particle. It could be a subtle change in how gravity behaves across billions of light-years, or new interactions in the dark sector, or a short-lived phase in the early universe we've never directly observed. And that's why NASA won't explain why feels true to people. Not because NASA is hiding data. These results are public and debated, but because there isn't one official why yet. There are competing hypotheses, and the evidence is still being built. This matters because the Hubble constant isn't trivia. It's a master dial. It influences how we reconstruct cosmic history, how fast galaxies grow, how structure forms, and how we estimate key timelines. It also affects the physics we trust. If the solution is new physics, it likely lives in the dark sector, where most of the universe's mass energy already hides. And here's the part that affects all of us. This is how science actually advances. Not by one telescope declaring victory, but by rulers disagreeing until someone finds the missing assumption. The hopeful part is this: we're not stuck. We're refining the experiment. Better calibrations, larger samples, improved lensing surveys, and standard sirens, gravitational waves that can measure distance without the same ladder assumptions, are all on the way. Every one of these is a chance to either crush the tension or prove it's the real deal. But this isn't the only cosmic crack showing up. JWST is also spotting early galaxies that look too massive too soon, and dark energy measurements are getting sharper and stranger. Hubble's last image might not be a picture. It might be a contradiction. Stay curious, and I'll see you in the next one.